Alright, it's time for Chapter 3, Motion in Two Dimensions and Vectors. We had talked before about what were the dimensions that we were discussing. And our first dimension is just motion in one dimension is what we studied last chapter. Forward and back, left and right, up and down. Well, now we're going to talk about motion in two dimensions, which is both forward and backward and up and down. For example, this human cannonball person is traveling in two directions simultaneously. They're traveling up into the air, which is a combination of forward and upward. So that's your two dimensions, motion in both the x and y axis. So topics that we need to address in this chapter are things called vectors and scalars. And you need to ask yourself, what is a vector quantity? What's a scalar quantity? Well, a scalar quantity is a quantity that has only magnitude, 3 meters per second. In comparison, a vector has both a quantity, a magnitude, and a direction. So 3 meters per second to the north. Now there are times when we will use a positive or a negative to indicate direction, and that's fine. See some examples. 40 meters per second, scalar or vector. I'm going to call this a scalar quantity because no direction was specified. 5 meters to the north. That's a vector because it has direction. 14 liters of gas. No direction, scalar. Negative 9.81 meters per square second, the acceleration of gravity on Earth. That negative indicates direction, so that's a vector. The velocity of a car. Velocity, by definition, has both magnitude and direction, vector. The number of pitches thrown in a baseball game. That's going to be a scalar. There's no direction on that. It's a number of pitches. Vectors, which are more important to us now, can be drawn as arrows. For example, if these two 2-meter arrows are lined up with each other, they are equivalent to one 4-meter arrow. We can add them up. See, they're equivalent to a 4-meter arrow. They can be lined up and added up. If they're going the same direction, you can add them. If you walk, for example, 2 meters forward and then 2 more meters forward, you walked a grand total of 4 meters. If instead you walk 2 meters forward and 2 meters backwards, that would be the equivalent of 0 meters. So they can subtract too if they are in opposite directions. Looking at an example, what if we took these directions on the grid? This line here represents, this resultant represents the overall displacement. Well, we can rearrange our vectors as need be. Let's start with our horizontal vectors. Bring them down here, and let's just try to line them up right on the grid. And when we do this, we always go nose to tail. Kind of like if you see old pictures of the circus, and the elephants are marching, and they're like holding the tail of the one in front of them. Nose to tail. Nose to the tail of this pink one. Nose of the orange, tail of the pink. Nose of this green one. Or I'm sorry, tail of the green one to the nose of the pink. And then tail of the blue one to the nose of the green. And then that represents all of our different lines. If we did this properly, we went 1 step, 2 steps, 3 steps, 4 steps, 5 steps. We'll go back. If we did this properly, I should be able to pick this resultant up, put it on the tail of the red, and it should connect to the nose of the blue. And this shows that within human error of lining them up wrong, it worked. Okay, we can rearrange our vectors algebraically and solve for their lengths. Okay, so what can you take from this? How about a homework assignment? The section review on page 83, 1 through 5.